So, good evening, everyone, and welcome. I'm Greg Slavaugh, Director of the Digital Environment Research Institute. Tonight, we gathered Queen Mary, University of London, to celebrate a significant milestone, the inaugural lecture of Professor Cedric John, a distinguished new member of our academic community. The Digital Environment Research Institute, or DERI as it's also known, is Queen Mary's flagship university research institute dedicated to pioneering advances in digital and data science. Established under our University Strategy 2030, DERI embodies the university's commitment to tackling global challenges through a multidisciplinary approach, uniting experts from diverse fields to work together to create innovative research. Aligned with DERI's strategic objectives, we are honored that Professor John joined us as Professor and Head of Data Science for the Environment and Sustainability. His remarkable work at the intersection of geosciences, machine learning, and deep learning puts him at the forefront of developing technologies that tackle some of the most urgent challenges of our time. Today, we celebrate not just Professor John's professional journey, but also the visionary insights he brings to our community. His professorship is a testament to the profound impact of his research on our understanding of the natural world and our pursuit of sustainable solutions. So please join me in warmly welcoming Cedric to the podium as we eagerly anticipate learning more about his journey to this moment and the science underpinning this research.
All right, thank you very much. Thank you, Greg, for the very warm welcome, and thank you everyone for being here today on this special day. It's an honor to see old friends, new friends, and friends to be. So the title of my inaugural lecture is Data-Driven Earth Sciences, and it's really about my journey from fieldwork to artificial intelligence. So whenever I'm asked to introduce myself professionally at a conference or with peers, I cannot use clickers. So there you go. Okay. I struggle a bit because the problem is in my career, I've been doing multiple things. So let's see if this works. Now, okay, we'll revert to old tech. On the one hand, I'm a field geologist. I'm an expert in carbonate sedimentology. Carbonates are sediments that come from corals. If you know coral reefs, they produce calcium carbonates, and that sediment is then accumulated and form rocks. So I've been doing a lot of this in my career. But at the same time, I can also describe myself as a geochemist because I've applied advanced geochemical tools and developed a stable isotope lab to measure the chemical composition of carbonates. Carbonates are chemical sediments, so we can tell a lot about what happens by measuring their isotopic composition. And of course, the reason I'm here today is because I also do numerical modeling, and over the last 7 years, my research has shifted heavily towards artificial intelligence applied to the earth sciences. So I have these three approaches, three different icons that I will show you during the talk to basically highlight what method is being used where. Now, when it comes to what I study, well, it's a little bit easier. So on the one hand, a big motivation for my research is climate and environmental changes. I can just show you some very recent events, the flooding in Dubai 2 weeks ago, and last summer we had forest fires in Greece. All of these are a consequence of climate change, which is of course triggered by our emission of CO2 into the atmosphere. So understanding past climate change and what the future of our planet might be is a big motivation for me. At the same time, though, I think that you can't just look at climate. You also have to look at energy. Because if you ignore this and you ignore the trends, so this is a plot that shows the world's energy demand. And the thing that is most striking on this plot is this. Since the 1950s, we keep increasing our demand for energy. So we live in a world that at the same time is warming, but also needs more and more energy. Now, part of that energy is coming from renewables. That's great, but it's only about 15-20% maximum. Most of it comes from essentially non-renewable fuels, mostly hydrocarbons, gas, and coal. And that's, of course, a problem. And I think that you really can't tackle the climate crisis if you can't tackle the energy crisis and help essentially the world to transition to cleaner forms of energies. So that's going to be kind of like the frame of my inaugural lecture. And because this is my journey, I'm going to talk about my career. So I thought the best way is to show you a timeline of my career and use this as a thread for the talk. So you see here, we have dates starting with when I was born. Who cares? That's not so important. All the way to today with some key milestones. But I know I have a lot of geologist friends in the room, and a timeline like this makes them very nervous and uncomfortable. So in parallel, I'm going to map my progression on a geological time scale, okay? And we're going to start with my Proterozoic and my Paleozoic, or my childhood and my early career. So I'll show you how things that happened in my childhood impacted my research direction, and we'll talk about my early career. Right, so I grew up in Switzerland, in the Jura Mountain. I grew up actually, part of my youth was at a kilometer altitude, so we had beautiful snowy winter, quite harsh, but it was really pleasant to be out. So I was really in contact with nature from a very young age. I'm also the eldest of a family of 4 boys, so that's me, the bossy older brothers. My PhD student will recognize that trait here. It's continued to this day. So why did I become a geologist? Well, part of the answer is kind of really very common. I love dinosaurs when I grew up. I had dinosaur toys, so I was really interested into this. But I was lucky enough to grow up in a region where I could actually go out and look at rocks. And in the rocks, I found fossils. And there I had from a very young age this realization that the mineral world was telling me something about the organic world of the past. And that's a powerful notion when you realize that you hold in your hand something that is, 120 million years old and tells you that there was an ocean and life in this ocean. But what sealed the deal was caving. At the age of 12, I discovered caving as both a sport, but also a science in some ways, because we did measurements in cave. I met some geologists, and I was sold. From that time, I was going to become a geologist. That, however, was not the only influence in my childhood. I have to credit my dad for also having an influence on me. And my dad is a physicist, so I was trying to find a physicist's photograph, and I think that's his Oppenheimer moment with the light. That's the best I could come up with in the 1960s. And my dad is a physicist, but he's a physicist who turned computer scientist before the term existed. So in the early 70s, he was exposed to computer science, and then he left academia and worked for the Swiss government as a computer scientist. And he was very keen on his sons learning computers, learning to code. So he really encouraged us to code, and he bought us a computer, and I really loved it. So if you looked at the early 90s, this is what you would call today my tech stack. It's completely outdated. That's okay. I've updated it. But I've learned really to code from an early age, actually from the age of 8. And for me, this was fun. And up to today, it is fun. You can ask my wife. I code on the weekend. She doesn't understand this. But anyway, I think it's really fun. So we'll see how this played a role in the future of my career development. So to my dad's greatest chagrin, I did an undergrad in geology and not computer science. It was really kind of 50-50, but I figured if I go computer science, I can always use my computer skills in earth sciences later. So I went to the local university, the University of Neuchâtel. And there I was very lucky that towards the end of my undergrad degree, I had a really good education, but also I met someone who was going to influence my career quite a bit, Professor Carl Furley, who unfortunately passed away in 2019. So Carl moved to Neuchâtel from the ETH Zurich, and he was a very modern geologist. And it was just at the time when I had to decide what to do for my master's. So I was very happy to work with him, and he convinced me, which was very easy actually, to work on the California Monterey Miocene Formation. I have family in California, so the logistics were fairly easy for me. But of course, traveling was always a big appeal for a geologist. But what was really significant with Carl is that he introduced me to the world of stable isotopes. So this is a pretty complex diagram. So I'll break it down for you and explain a little bit what you see here. So at the top, the black line here is oxygen isotope. This is measured on foraminifers, which are single-cell organisms that precipitate a calcitic shell, okay, tiny shell. Oxygen isotope tells you something about the temperature of the ocean and it tells you something about the volume of ice that you have on the continent. It actually tells you both, which is a bit of a problem, but it's a double signal. At the bottom here in green, you have carbon isotopes. Okay, carbon isotopes are actually more tricky to interpret. Really, what they tell you is where in the world's reservoir carbon is being stored. But to make it simple, you can think of it as how much carbon is in the atmosphere. This is how we're going to interpret this plot. So the thing you have to know if you're not a geologist is that we look at deep time. We like to look at things that are very old. You know, if you show us something that's 100,000 years old, we're like, yeah, that's yesterday. So this plot here shows time in million years, and we always look at time backwards. So we're looking at a time period that goes from 17 to 11 million years in the past. And that's part of what is known as the Miocene. What's interesting in the Miocene is this so-called Monterey excursion. So what's the Monterey excursion? The Monterey excursion is a broad positive peak in carbon isotopes in carbonate, also with smaller peaks of carbon isotopes, positive peaks. This is interpreted as essentially withdrawal of carbon from the atmosphere. The partial pressure of CO2 in the atmosphere is decreased. But what's really key here is that if you look at the correspondence with the oxygen isotope record, we see that these spike in carbon isotopes, so spike in removal of carbon, correspond to glaciation. And this is actually a permanent shift in the state of the world, where we go from a world that's partially glaciated to a world that's much more glaciated at the end of it. So between these two dates. And so less atmospheric carbon means, you know, glaciation on Antarctica. And you can imagine that when I started working on this as an impressionable master's student, this was a revelation because I had found a tool that I could use to basically investigate the past and understand past climate change and the relationship between atmospheric CO2 and climate. So after my master's, I moved to Germany. I became an expat, which I still am, although technically I am now a British citizen, so I'm not an expat anymore. But I moved to work with Maria Muti at the University of Potsdam, and Maria is an expert in carbonates. So that's where I learned my carbonate skills. But which is equally significant, Maria was also very well connected to the ocean drilling program, known as the IODP. So the ocean drilling program is essentially a research program that's been going on for 56 years now. Very sadly, it's going to stop this year, but it's been the longest earth science program and one of the most expensive. And essentially what we do in the ocean drilling program is we take a ship, the JOIDES Resolution in this picture, and we go all around the ocean. And you see those dots on the map, they represent places where IODP has drilled, okay? And this is all for science purposes. There is no oil and gas here, so it's just for research. So what does it mean drilling? Essentially, here you have the three platforms or existing platform of IODP. When you drill, you basically send a steel pipe through water. So that could be 2 kilometers of water, that could be less, that could be more. And into the sediments, you can either use a piston, so pressure, or you can rotate the drill bit. But what you do is from the seafloor, you start to recover material. The material that you recover is called a core. And here I'm showing you a core section. And what I want to point out, because it's relevant for the rest of the talk, is that this is a 1D view of the world. Okay, so we have a 1D view of the sediments in the seafloor or of the hard rock in the seafloor. So I was able, thanks to Maria, to join ODP as a grad student. So this is me looking much younger. Okay, this is during my PhD on the Marine Plateau, ODP Leg 194. And one thing that's amazing, so you have a few pictures here of different expeditions I've been on, because subsequently to my postdoc, I actually worked for IODP for about 3 years. But what's really important to realize is we go out at sea for 2 months and we work 12-hour shifts. And there's a night shift and there's a day shift. And it's a program that makes young scientists, which was me at the time, no longer, sadly, but I was a young starter, and much more senior scientists. So here's Gary Carter from Lamont Doherty Earth Observatory, a very famous scientist even back then in 2001. And him and I became really good friends, and we worked a lot on quantifying the magnitude of sea level changes during my PhD, but also way beyond my PhD. And that was, again, someone who became a mentor and a big influence on my career. But getting back to the research and, not just the human component here. So what were we doing? So to understand this, you have to understand Antarctica. So if you look at Antarctica today, we have this beautiful glaciated continent. But if you were to remove ice, which by the way, we're doing very well, very fast at the moment with CO2 increase, you'd get something like this, okay? And immediately you can see that Antarctica really has two different provinces. So in the west, we have the so-called West Antarctic ice sheet. And if you look carefully, you'll see it's a bunch of islands, they're volcanic islands, and seawater. If you melt the West Antarctic ice sheet, you get about 6 meters of sea level rise. It's dramatic, but it's nothing compared to the East Antarctic ice sheet, which is a landmass. So all the ice on that landmass would contribute to sea level rise. And when I started my PhD, we still had the question of when was Antarctica glaciated, and more importantly, by how much. And if you could quantify sea level change, global sea level change, not just locally, you could actually answer this question because we knew the ice had to be on Antarctica. So that's what we set out to do with ODP-led 194, which I was very lucky to sail on because it's offshore northeastern Australia, just offshore from the Great Barrier Reef. And I'm showing you here a seismic image. So what's a seismic image? It's an acoustic view of the subsurface. And this is the best way we geologists have to tell what's happening on the ground in terms of the lateral geometries. What's interesting on this seismic image, and the reason we went to that particular location to get cores, is this surface, okay? This surface shows a carbonate platform on your left, okay? And you have on your right the slope of that carbonate platform. And carbonates grow close to sea level. So we knew that in the Miocene, this was close to sea level. And here we have a second surface that represents a low stand ramp, or in other words, a low stand carbonate platform. So between these two surfaces, sea level had to have dropped. And if we had a way of measuring this distance between the two surfaces, we could tell by how much sea level had dropped. Okay, you had to do some calculation called backstripping to account for compaction and decompaction, but we had a geometric mean of reconstructing sea level changes in the Miocene. And that particular region was interesting because there was not too much tectonic. So that's what we did on the ship. We published a few papers, but I kept working on this, and I'll show you the latest iteration of this work, which we published in 2011, and Gary was involved with that publication. So here what you see is meter eustatic fall. Eustatic is global sea level versus age. At the top, the dots is the curve, the existing curve, it's called the Miller curve, and those zigzaggy lines are our own reconstruction. And what's important is to realize that what we did here is we paired estimates from backstripping, so geometric estimates, with stable isotope estimates. So we meshed here both the field geology and the isotopic composition of foraminifers. And our conclusion, and I still stand by it, is that sea level must have fallen anywhere between 54 to 69 meters if you look at the overall time span from 17 to 13.8 million years. And that's much more than what previous estimates had thought. Now, of course, if you were to melt that ice, you'd have that much sea level rise as well. Right. So that brings me now to my postdoc. So during my PhD, I learned a lot about times when the Earth was getting glaciated. I was very keen actually to learn also about periods when the ice was warmer, or when the world was warmer, or when we had warming events. So I went to UC Santa Cruz to study the Paleocene-Eocene terminal maximum, and I know there are some slugs in the room, so I'm not alone. And what is the Paleocene-Eocene terminal maximum, or the PETM? It's a climatic event that happened 56 million years ago, and again, we can go to isotopes to explain it. So here you have carbon isotopes, and here what you see is a shift towards more negative values. So that tells us the reverse. Carbon was released into the atmosphere, and it's anywhere between 3,000 to 7,000 gigaton of carbon that went into the atmosphere. Sure enough, if you look at the oxygen isotope, we have a massive warming. The deep ocean warmed by anywhere between 8 to 12 degrees Celsius, which is enormous. This is my postdoc supervisor, Jim Zappos, who's a big surfer dude. So that's why he's in a neoprene suit in the ocean. I can see you laughing. But what's important is that he was a core here. It's actually a fake core, but it's a model of a real core that he was on the ship and recovered with his team. And what's important is it encapsulates the PETM. And this core comes, if memory serves, from 1,500 meters below sea surface. So it's from the intermediate ocean. And it has at the bottom white sediment, which indicates carbonate. And that's typical for this kind of depth in the ocean. But above, what you see in the same interval here is much darker sediments. That indicates no carbonate. It indicates that the carbonates were dissolved, okay? And so this is like evidence that at the PETM, the oceans were acidified. The CO2 was released from probably methane clatrate, went into the atmosphere, was oxidized to CO2, re-entered the ocean, and that lowered the pH of the ocean, which is something we see today, okay? And when you do this, the problem is, okay, you dissolve carbonates, but also you make it very hard for organisms that rely on precipitating a shell made of calcium carbonate to survive. And at the PETM, we see that there's anywhere between 30 to 50% of benthic foraminifers that went extinct. So that even had some consequences. It also had some consequences on land. We have lots of evidence for increased storminess, for lots of precipitation. The Arctic Ocean was tropical to semi-tropical with crocodilian living there. So a very, very different world. And you might think this is science fiction or the deep past, but here's the scary bit. If we keep producing CO2 into the atmosphere at the current rate, we'll be there in 2159, 2278. Don't worry, kids, it's not you, but it's the generation after. So it's really, we're looking at a potential analog here for what we're doing. So when I started my postdoc, this was already well understood. What was less understood was how the world recovered from the PETM. So that's the good news. The world recovered naturally from the PETM. The bad news is, it took 150 to 220,000 years, okay? So be patient. So my postdoc was about understanding this recovery, and to make a long story short, I think that what happened was that we started to trap a lot of organic carbon on continental margin. We had increased sedimentation rate on continental margin. But I was told by Greg I have only 1 hour, so I cannot cover every day. Okay, so that brings us to the end actually of my early Paleozoic, my early career. Just to also mention that after my postdoc, I stayed in the US and I went to work for the Integrated Ocean Drilling Program for nearly 3 years, which was a great experience. So I've learned a lot from this experience. I became a marine scientist, a paleoceanographer. I learned a lot about stable isotopes, carbonates. I did some field work. And of course, I worked on paleoclimates. And then in 2008, I was lucky that I applied and was offered a lectureship position. In fact, Martin was the head of the department at the time at Imperial College London. So I became a lecturer, and then I actually stayed at Imperial nearly 16 years. So I was promoted to senior lecturer and to reader. So now let's explore that second part, what I call my mid-career or my Mesozoic, for those of you who are geologists. So my former department, the Earth Science and Engineering at Imperial College London, is very well known for its work on the energy transition and essentially on energy. And one thing that I had no clue about when I joined, I learned very fast, is this thing called carbon capture and storage. So here I move my research from understanding climate to potentially doing something to mitigate climate change. So what is carbon capture and storage? So first of all, it's a realization that if you look at the energy mix today, there's no way we're going to go all green, in a matter of 10 years, right? So we need to find a solution, an intermediate solution to avoid putting those emissions into the atmosphere. So if we could capture emissions at large facilities like large power plants or oil-producing rigs, and if we could compress that CO2 to a supercritical state, and then re-inject it into the formation, into the subsurface, then that CO2 never sees the atmosphere, it's never released into the atmosphere. And that's carbon capture and storage in a nutshell. And when I joined Imperial, Martin Lunt, who's a reservoir engineer, and Jeff Maitland, who's a chemical engineer, invited me to collaborate with them and essentially be the PI on a geology part of a grant to do carbon capture and storage in the subsurface of Qatar. And this was a massive grant that basically fed us and clothed us for 10 years. Thank you, Martin. And we did a lot of interesting research at the intersection between earth sciences and engineering. So the thing that's interesting about CCS as a geologist is that you have to make sure that if you are going to inject CO2 in the subsurface, it will stay there, okay? And to ensure this, you need to understand what the heterogeneity, in other words, what the lateral change in the formation is. And you've seen a core now, and I pointed out it's a 1D view of the world. A 1D view of the world will not do. Seismic lines are 2 or 3D, but they're not at a very high resolution. So the only way we can get good handle on heterogeneity of rocks is by looking at them at the surface, where they crop out. We call this outcrop. So that part of my career became really dominated by 10 years of doing outcrop geology and visiting many places in North America, Europe, but especially in the Middle East, which is a place I fell in love with for the culture, but also for the geology. So again, I have only 1 hour, so I'm going to show you only 2 examples of the type of fieldwork we did. But fieldwork, you know, a lot of geologists become geologists because they want to go out and be in the field. And there's a saying that the best geologist is the one that saw the most rock, and there's some truth to it. So definitely in 10 years, I've seen a lot of rocks, especially in the desert, because, you know, the desert has no vegetation, so it's perfect, right? So you can see all those rocks. But it's not just about, you know, the science, it's also about the human components of fieldwork. So I was lucky to work very closely with John Cosgrove, which I think is one of the world's best structural geologists, and I learned a lot from him being in the field and collaborating with him very closely. And sure, fieldwork can be challenging. If you have a flat in the middle of the Omani desert, it can be life-threatening. However, we always went safely. Martin, don't worry. And we had multiple cars, so it never really was an issue. So overall, a very positive experience. So I'm going to show you 2 examples. My first one is Jebel Madar, one of my favorite location and where we did a lot of work. So you can see Jebel Madar is this domal shape. It's about 8 kilometers by 5 kilometers to give you a sense of the dimension. And it's a dome because in the subsurface you have salt, and that salt is less dense than the surrounding rock. So it pushes up towards the surface. It's not pierced here at Jebel Madar, but that push up basically triggers a bulging of the rock. And you see in the middle of these valleys, these are fractures. They're basically opening up, cracking, if you want, of the carbonates here at Jebel Madar. Salt domes are very common in the Middle East, and they're potential good targets for CCS. So we were very curious to understand this fracture network and understand what's in the fractures. And that's why we did so much work there. So let's go have a look at this Jebel from close up. And the lizard is just here as an eye candy, so it's distracting. But you also do see some wildlife in the field. But what I really want to show you is this. These are minerals of calcite, and they're about 30 centimeter big. So they're really, really impressive, and they're everywhere. They litter that Jebel everywhere. Now, calcite is a very common mineral. It's a calcium carbonate. What's less common is this. This is barite. Okay, barite is a barium sulfate. And I had never seen barite at the outcrop. And now that barite is only in a few places at this location. But when we find it, it's massive. It's really, really big deposits of barite. So we were really curious to understand the relationship between the fractures and the minerals and, you know, the process, what triggered the precipitation of those minerals. So the field is great because it gives us a lot of indication of the distribution of these phases. It gives us a sense of the geometry and the cross-cutting relationship between the fractures and the minerals, in other words, relative timing. So it's very, very useful, but it's not the fingerprint of process that we needed. So again, you have to pair something else, and you'll guess it, it will be stable isotopes. So at Imperial, I actually built my own lab, starting in 2009, and with the help of Simon Davis, who was my lab manager. And we didn't just do a stable isotope lab that does carbon and oxygen. We actually started to do something a little bit more tricky called clumped isotopes. So what is clumped isotopes? So clumped isotopes look at the clumping, hence the name, of carbon-13 and oxygen-18. Those are both rare, heavy species, so their presence together is extremely rare. And that's why clumped isotope is difficult to measure, because we're looking at something, a signal in the order of 40 ppm. Okay, so it's a very difficult measurement to do. But if you manage to do it, the reward is that this is a one-phase paleothermometer. So essentially, you can tell at what temperature a mineral was formed, and by extension, then you can calculate the composition of the fluid. So one of the problems with clumped isotope when I started was that the calibration stopped at 70 degrees, right? Because in a lab, if you try to go above this, you have evaporation, it gets messy to do precipitates. The issue is in the subsurface for CCS, we needed to go to higher temperature. So with my former postdoc, Tobias Kluge, we actually managed to do an apparatus that controlled pressure, and we had precipitation up to 250 degrees Celsius. So we pushed that calibration quite a bit, and now it was useful for subsurface application. So let's get back to Jebel Madar. I'm going to show you just one example of clumped isotope today. So in Jebel Madar, what we see when we analyze those minerals is this, and that's the work of Adib Erlamoun, my former PhD student. What we see is basically two groups. One that we call trend 1, that corresponds to the barite calcite association. Now that barite calcite precipitate at very high temperature, up to 160 degrees and down to maybe 80 degrees. There's a range. Okay, and the fluids are much heavier than the other trend. What that tells us is that this was probably put in place very deep in the subsurface when the Jebel was just starting to form. So those are the early fracture. And now we understand why we only find this barite association in a few places. It's the early fractures that are preserved. The calcite, however, that litters the whole Jebel is much colder, anywhere between 80 to 50 degrees. And the composition is much lighter. And what it tells us is that this is probably meteoric fluid. In other words, rainwater that percolated through the fracture network, was heated up and precipitated this hydrothermal, essentially cave deposit. So through this, now we can say that if you're looking at the subsurface for injection of CO2, you don't have to worry about the calcite. It won't be there. You do have to worry about the barite. Okay, so that's how we can use this fingerprinting mechanism. And now the second example, and I'm actually very happy I chose this one because this is from Martin Hönig, who's here. He flew all the way from Germany to come to this lecture. He must have known. He always was a clever one. So I showed you what we did with fractures. That was one of our concerns. Our other concern was actually bedding. So essentially the sediments, how they were deposited. So this is now an outcrop in the UAE, in Ras Al Khaimah, and it's called Wadi Nakha. And at this particular location, what we have is a beautiful outcrop where we can follow laterally bedding for 1.4 kilometers and up to 130 meters vertically. So we have a really good view on the beds, okay? And the outcrop is Jurassic in age, okay? So 140 million year, give or take. What's really remarkable is that if you follow those beds, they're continuous. I think there's one pinch out that Martin could find on the photo mosaic, but all of the other beds are completely continuous, okay? And this is actually quite well known in the Middle East, right? There's a term for it. If you ask a reservoir geologist in the Middle East, they'll say, well, this is layer cake, okay? So that's a layer cake geometry. And the bias of layer cake is to say, because it's the same layer, it's the same property. So if I have a 1D view of the world with a core, and I know the property of the rock at the core, I just populate my reservoir and I inject my CO2 and I don't worry about it. But with Martin, because we had access to that outcrop, we could go and check this model, right? We could see if really it was the same thing laterally. And what we did is measure a lot of sections and then correlate those sections because we could follow the bedding. And I'm sure you can guess it. What we found is it was nothing homogeneous at all. In fact, when we had sediments that were deposited into high energy with lots of wave, actually they were not continuous. Even though the bed was continuous, the property of the rock changed. And if that impacts the flow property of the rock, then that really matters for reservoir. So typically we would not stop there at the outcrop, but we do then with these data. Because we have the statistical distribution on the rock, we can actually build model, either a statistical model. This is the work of another one of my PhD students, where we do geostatistics with Thomas Leblanc, or we can do forward modeling. But you can see this is a dangerous slope now because we're going into the numerical methods. And the one thing I've talked a lot so far, but the one thing I've not really mentioned is how I went from doing fieldwork and geochemistry to integrate AI into my research. And so that's going to be the next thing we'll explore. Why and how did I integrate AI into my research? So you can already realize that geology deals with a lot of unstructured image analysis, right? And that was really the key, because now we're going to get a little geeky. If you look back in 2012, there was a paper that came out by Alex Kizevsky et al. That basically proposed a new architecture of convolutional neural network. What's a convolutional neural network? Well, it's a neural network, so an AI algorithm that is composed of convolutional filters. So these basically extract features from images or other unstructured data. And then at the back, you have a very normal neural network that does the classification. Now, convolutional neural networks, CNN in short, are nothing new. They were already around in the 80s, okay? But what was interesting in this particular AlexNet is that it was head and shoulder better than the previous ones. Why? Because that's where we get really geeky. They integrated new technology like the redo activation function. They also were able to run on multiple GPU. And they were also doing this thing called overlap pooling. In short, they were just much faster, okay? And because they were faster, they were able to analyze not just toy data set, but real data set. So we see here the evolution from this being mostly a computer science exercise to potentially being interesting for other fields of science. And AlexNet really triggered a plethora of inventions, with new technologies in CNN being invented every 2 months. I'm showing you VGG19 here, which is still actually an architecture that's widely used, and takes a lot of its inception from basically the AlexNet. And at the time, of course, I knew how to code. I was looking at this, I was very interested, and I could see that in the medical domain, they were starting to apply computer vision to medical imaging. And for once in my career, I was ahead of the curve, ahead of the trend, and I thought, what if we do this for earth sciences? And I thought I had the perfect case study to try. So what was that case study? Well, to understand it, you have to understand how we carbonate sedimentologists classify rocks. So what you see here is a thin section. Think of it as a just a microscopic image of a rock. It's about 13 micron in thickness. And this particular thin section is classified as a wax stone, which is the texture of the rock. So we use texture of the rock as the name for this rock, and there's this Dunham classification that we use. The rationale behind this is that if we understand the texture, we understand what energy the rock was deposited in, the sediments were deposited in. So this particular study is by my friend Stephen Lockyer and his student Janabi, published in 2015. What they did is they created artificial thin section, but we didn't know they were artificial. But that's important because they controlled the texture. So they knew the texture very well. So that's why they know this one was a wax stone. They created 14 thin sections. They took photographs of those thin sections, and they sent them to 177 carbonate sedimentologists. And the question was very simple: is what is the texture of this rock? The answer was not simple. That's what came up. I'm showing you just this one thin section, but all 14 of them are similar. And you can see that we came up. I have to say, Martin and I, we were part of that study, so we take our blame here. But we came up with very different names. A lot of them were kind of correctish, wax stone, but a lot of them were completely wrong texture for that particular rock. And what was worse is we were asked whether this was a hard or easy rock to describe. We nearly all said it's easy peasy, okay? And that's actually a well-known problem. This paper just essentially highlighted it very clearly, but we have a problem when we describe things, especially as teams. We have this descriptive bias where we tend to not really do a good job at describing things, especially if we have to do it for a long amount of time. I had encountered this on the show. So long story short, I thought maybe this is a case where convolutional neural network can help us to do this. So I've done a master's project, and then I moved on to a full PhD project when the results looked promising. And I'm going to show you the results from my student, Harriet Dawson, who has just submitted her PhD, and this was published last year. And I'm skipping all the methods, because that's not interesting. I'm going straight to the result, because that's the cool bit. So to understand the results, you have to understand a confusion matrix, okay? So here you see the confusion matrix of our test set. So this is data we did not use to train our model. That's super important, otherwise we cheat, right? It's easy to predict what you already know. A confusion matrix is a double entry table, all right? So on the vertical axis, we have the actual texture of the rock. And on the horizontal axis, we have the predicted label. In other words, what our machine learning model tells us the rock is. So you can see we can put all of our prediction into that double entry table and present it as a matrix. We present this as a heat map. So the darker the blue in this heat map, the more samples proportionally fall into that particular tile. And what's really important is this diagonal, okay? Because this diagonal, think about it, is when the actual label and the predicted label are the same. In other words, when we make a correct prediction. And you can see that the machine learning model is doing very well because this diagonal is dark blue. And in fact, most of our classes are above 90% correct prediction. There's just one, the floatstone class, which is the second last, which is at 87% prediction. It's actually a very hard one to distinguish from the next class, which is redstone. So the model makes 10% error in that thing. Okay. But on its own, that's not so interesting. What's interesting is to compare the Lockyer and Genevi study, because they've published their data. I could plot it as a confusion matrix, and we can compare the human confusion matrix to the machine learning confusion matrix. And immediately you can see it's not looking so good for the humans, right? Because we are a lot off from the diagonal, so we make a lot of error. There is kind of a diagonal, but it's not so good. In the middle, I'm showing you basically everybody who took part in this study. On the right, I'm showing you people who are self-declared experts, so level 4 and 5. Long story short, there's not a lot of difference between everybody and the experts. But what's super interesting is really to look at the flowstone, redstone, the last two classes. You can see that we humans do terrible on these. And it's because these two classes are defined by 10% of your grain being larger than 2 millimeters. And a machine can do this systematically very well. We tend to not be very systematic with these very quantified metrics. So the take home here is that a machine learning model might be biased, probably is biased. I'm not saying that our model is completely correct, but at least it's systematically biased. So if you're going to be applying this machine learning algorithm to 10 locations around the world, you can compare your data, even though it has a bias. Whereas if you use human for description, you cannot compare your data. And we had that problem actually on the ship I was on, where the night shift and the day shift had totally different names for the rocks. And that was a problem because we had sea level cycle until we realized they were not cycles. Okay, so moving on to a second example of how I think AI can help us is one thing I've not told you is that when we recover core, especially in carbonates, we don't always, or very rarely, recover 100% of the core, right? Because carbonates are very friable, so when we drill with the rotation, we tend to destroy some and only recover some of it. And in fact, this is two wells here that I show as an illustration. Here, this is called the recovery column. What's black is the proportion that was recovered. What's white is the proportion that was not recovered. So you can see we're recovering about 20 to 30% of the rock. It's a terrible recovery here. Luckily, there's something we can do. Once we have the well, that's so basically a hole in the ground, we can send tools to measure the property of the well. And that is then a continuous record. So, but that saves us because we can now look at the entire well. In particular, one tool that is very useful is the formation macro scanner. Fancy name. What it does is it basically looks at the resistivity of the rock to electricity. And that gives you a pseudo image that you can then use as a tool to interpret the subsurface. So that's how it looks. This is, you see here 4 tracks, which represents the well if you were to unfold it in the 4 tracks. And you can see it's like an image, but it's an image of resistivity. It's not an image of, taken with light. And it's great because it's continuous, but it's also problematic because I cannot interpret this. I mean, I have 20 plus year experience as a geologist, but you really need to be trained on these particular images to be able to read them. And so with another student of mine, Sarah Baroudin, what we tried for her PhD was to use generative AI. So you all know ChatGPT. This is not ChatGPT, but it's the same idea but for images. We thought, what if we use generative AI to basically transform the FMS image into a pseudo-synthetic core image, because that geologist, I thought, could interpret. The particular technique we use is known as a GAN, or a generative adversarial network. If you're really into machine learning, we actually use speaks-to-speech HD for this particular work. But the real question is, does it work? And so I'll let you be the judge. So this is, after years of work, the results from Sarah. So on the left, you have the actual core images. So these are real core. And on the right, you have the reconstructed core images, synthetic cores, reconstructed from starting with the FMS data from that same core interval. And you can see for the first two cores, it looks remarkably similar. The third core looks similar, but I'll point out, you see those big patches in the real core? They're called rhodoliths. They're kind of algal structures. We tend to smooth them out. We don't see them as well. And I think that's going to be important for the next bit of the talk. So what we did now is to ask the question, does it actually make a difference? Is this technology actually useful? And for this, the best thing was to use my favorite guinea pigs, also known as my research group. And what Sarah did is she gave them 25 image of real cores. So these are little thumbnails, image of the real cores. And they were asked, what's the Dunham texture? What's the texture of this rock? And guys, you can be proud of yourselves because you did pretty well. This is your confusion matrix, better than the experts in the Genevi, Lockyer and Genevi study. We see a nice diagonal. It's actually a pretty good description. 87% accuracy. They can describe cores. Great. These guys, however, are not trained to interpret FMS data. So let's give them FMS data and let's look at their confusion matrix. Well, no diagonals, okay? In fact, this is 5 classes because that's all we had, and we get an accuracy of 14%. That means it's random. You're guessing basically what the texture is. So really, the proof in the pudding is this. Now we take the FMS data. One thing I forgot to mention, the real core and the FMS data are the same, okay? They're not different. So they're the same, the very same registered interval. And from the FMS data, we generate a pseudocode. And again, same question, what's the Dunham texture? And now look what happens. From the same FMS data, after using generative AI to turn it into a core, we're back to having a nice diagonal. Our accuracy is down to 73% instead of 87%, so we lose 14%, but it's well beyond what we can do with the FMS data. So it really helps geologists interpret this data. And better yet, we can understand why we're not getting the same accuracy. If you do an error analysis, you can see that systematically, we have essentially underestimated the coarser textures. Okay, so the coarser textures are estimated as finer texture, and I think it's because our algorithm can still be improved, because I showed you that we're losing some of these large grains. All right, okay, so that's kind of what I did at Imperial College. So what I've learned, of course, is a lot of clumped isotopes, CCS. I learned about basically doing something at the intersection of engineering and geoscience to not just understand climate change, but maybe even help, mitigate climate change. But this is also where my coding as my childhood finally came into play. I was right. I was going to be able to use my coding skills in my work just 20 years later. But anyway, I've learned geostatistics, numerical modeling, and I became an expert in deep learning. And this is why I'm here tonight, right? This is why Greg hired me, is to basically be a professor here at DERI, the Digital Environment Research Institute. So that's right. I was very happy to join DERI, but I have to say I feel a little bit guilty because a month after I left, this is what happened. Imperial College London became Imperial. I think the place is not the same without me, is it? Well, jokes aside, what I want to talk about now is the future, what lays ahead. So I've been only 4 months at Queen Mary, so I don't expect a ton of new research, but I can show you current trends. So of course, I keep doing the same type of research that I used to do. In particular, I'm still interested in sea level changes. I'm the PI on a grant from NERC to go and acquire new seismic data. We think we're going to be able to sail in 2026. It depends on when NERC will partnership with the US. And this is about imaging guyos from the Cretaceous, so about 100 million year old, and reconstructing sea level changes. There's also an AI component where we're going to try to basically improve seismic imaging. So again, seismic is this acoustic signal. And at the moment, we're working on seismic. So Walid Al-Abarbi, who sits here in the room, is doing work on essentially trying to automate the interpretation of seismic data. So that still is an area of research, and actually it's an area of research that will grow because I'm lucky to have a new postdoc starting next month, Haifa Al-Salmi, who's also in the room, who is an expert in AI applied to seismic. But I also diversified a little bit, and I now work on satellite imagery as well with my students. So Ziad, also in the room, Ziad Al-Zahir, is working on using satellite imagery of Earth and imaging coral reefs, modern coral reefs. And he uses unsupervised learning algorithm to try to recognize the different environment of deposition through time. So we're talking here decades, not millions of years. So it's a big change for me. Basically, the goal is ultimately to be able to see if we're going to have warping events. What's cool with satellite is we have them on Earth, but not just. We also have them on other planets. So also in the room is mapping minerals on Mars. Using their hyperspectral imaging. So you can see that AI brings you to a lot of places. And I think this is also a big area of growth for AI. Now, new place means new colleagues and new opportunities. And I've been here only 4 months. However, it's a very warm and welcoming community. And I've already made a lot of contacts with people who are keen on working together. So I'll mention a few groups. Sorry if I forget you. But first, of course, there's the geography department where I have fellow geologists there. And we've already talked about doing some work together on climate change and AI. So that's kind of my comfort zone, if you want. But there is a very multidisciplinary place, which I really enjoy. I enjoy doing multidisciplinary research. And I've already submitted a couple grants, actually, with the Digital Twin for Sustainable Development Goals. Notably one where we look at solar energy, adoption of solar energy for cleaner transport. So very different from my traditional roots. I also have met some old friends from Imperial, Edo Gok, which you guys will remember. And we talk about doing some work on hydrothermal energy. We've also submitted a grant on systems approach to net zero. But what's interesting is Queen Mary is very strong in the medical field. There's a big medical and dentistry school here. And I was very happy to make contact with Tina and others in the School of Medicine, and we're actually going to look at the intersection of pollution, AI, and medicine. And in fact, we have a master project starting over the summer. And last but not least, another thing that Queen Mary is well known for and is very strong is biodiversity. There's a very big biodiversity group, and we've already talked about AI for biodiversity, and there's really active people in this domain, and we're basically working at, basically getting funding and doing some work together. So that brings me to the end of my lecture, but of course I owe some thanks to a bunch of people. So I want to start first by thanking my family, my very blended family, because being an academic, you don't learn much, you travel a lot, and you actually work a lot. So you guys are putting up with a lot, and without your support, this would not be possible. Then I would like to thank the DERI team. So Greg, of course, who you know, because he introduced me, who's a great leader. It's really a nice place to work at DERI. But I have to say, without Emma or Janet, nothing would work at DERI. So we have fantastic support. In fact, Janet cannot be here tonight, but without her, I think it's fair to say this lecture would not have happened. And then, okay, it's all nice to be at a research institute, but if you don't have support from the top, it means nothing. So I'd like to acknowledge here Professor Colin Bailey, who's the president of Queen Mary, and Professor Andrew Livingston, who's the vice provost, research and innovation. He's in the room. He's also a former Imperial, so it's part of the family. And these guys really believe in the research institute and basically support this initiative. So thank you very much. But I think the biggest thank, to be honest, that I have to give is to my research group. You know, my former student, my former postdocs. I've introduced some of them. I've introduced, and also my current postdoc and current PhD. But I wanted to try to put all of them here on one slide so you can see their faces. And really, without their work, their dedication, I would not be presenting any research here, right? So let's not forget this. And that's it for me. Thank you very much. And I'm happy to take any question unless you'll rather have a drink. Good.